lab report. Here's the introduction. I used a scratch paper to make a paper ball, and the paper ball was released from rest and fell toward the ground. There are three physics principles. The first one is the drag force equals to b constant times the velocity squared. And the second one, net force is equal to gravity plus the drag force. And the third one, final velocity equals to initial velocity plus net force divided by m times delta t. And the lab report is that the model with drag predicts the terminal velocity of the experiment better. And let's first look at the tracker. I track the center of mass of this paper ball, and I derive the y value here, derive the experiment data. And then let's look at the computer model. The first one is the computer model without drag. I changed the mass of the paper ball here, and I changed the initial velocity. I derived that from the experiment data, and I changed the initial velocity to a zero vector. I keep the b constant 0, and the net force is just the gravity, negative mass times g. And here I use the final velocity equals to the initial velocity plus net force divided by m times delta t. And use the velocity times delta t, I derive the current position. And then let's talk about the computer model with drag. I keep the initial condition here, and I change the value of b. I test with different value of b and see for which value of b the computer model predicts the terminal velocity the best. And the net force is the gravity plus the drag force, b times the velocity squared times the direction vector j hat. And here I use the final velocity equals to initial velocity plus the net force divided by m times delta t. And use this velocity times delta t, I derive the current position here. And I put all the data on a spreadsheet and derive two diagrams. And let's analyze this diagram. Let's first talk about the similarity. The end of the blue line matches the end of the red line. That means the model with drag predicts the terminal velocity of the experiment better. And then let's look at the differences part. The yellow line departs from the red line further and further. That's because of the effect of drag force. As the velocity gets bigger, the drag force gets bigger, so we have greater discrepancy here. And also, we can see there is a tiny discrepancy between the end of the blue line and the end of the red line. We can use a formula to calculate the drag force better and try to eliminate the small discrepancy here. And for this formula, I derive it from Wikipedia. And C is the drag coefficient, rho is the density of the fluid, the A is the cross-section area of the object. And I've already answered the what does it mean question. Model with drag predicts the terminal velocity better. And for the what if question, I changed the initial velocity from a zero vector to a non-zero vector, 0, negative 0.5, and 0. And from Newton's second law, we can notice that when we increase the initial velocity, the final velocity gets bigger. And that is shown on the graph. The slope of the green line is greater than the rest of the line. That means the velocity is greater. And we also need to pay attention to the drag force. When we have greater velocity, the drag force will get bigger. However, since the b value is really small, like 0.009, the effect of drag force is not obvious on the graph. Overall, we still have a greater velocity. And for the conclusion part, I repeat the result. The model with drag predicts the terminal velocity in experiment better. And for the improvement part, as I mentioned before, I can calibrate b constant using a formula instead of the randomly testing. And I can use a sphere instead of a paper ball to better track the center of mass and get more accurate result. Thank you.